Reminders, your assignment is due next Thursday, anytime on Thursday of next week. You're going to post it to the assessment folder in OneNote. There is a spot for you to post it. It says, post here, and thank you. And you're going to put it in there as a printout. And then our test, which I told you was going to happen after the long weekends, falls on the Friday of that week. So after the long weekend is the 14th, so 2 weeks from today. Yep.
I have a calculus test on Monday. Should I speak to you?
Yeah, we can talk. Yeah. So we skipped over lesson 4 in part because I forget, but it is a bit of a challenging lesson, and ideally everyone would be here, but I'm just going to record this and they can watch the video. So you guys at home can watch the video. This is like the beginning, this lesson, of what's a big branch in stats that's more advanced analytical techniques. That's in an area that's called hypothesis testing. And it's quite useful, and it's used in a whole variety of different situations. And if you go on, for example, and do a master's in school, it's likely you're going to use some sort of stats in a master's thesis. Almost always, especially in science area, but also in sociology, you often use stats. This is one of the things you might use. It's not applicable in all scenarios, but it is in a lot of them. We're going to go through the understanding of it, but ultimately, like I said, you're going to do a lot of it just on your calculator. And to be honest, a lot of people who do their masters don't necessarily understand everything behind the stats. They just apply it, and they understand that part of it. And that's ultimately what you're going to do as well. So often in two variable statistics, you get data, but it's not easy to show something by graphing it. Like, for example, you could have categorical data. You can't make a correlation coefficient or anything like that. And you want to apply something different into it. For example, if you look at this data here, this is a survey of 400 students. And it asks those 400 students their gender, and then whether or not they exercise regularly. So for example, 3 or more times per week. Often we categorize people by age, gender, socioeconomic background, things like that, and look to see if there's any relationship between these things. So imagine you got the results, and here are the results. 110 males said they regularly exercise, 106 said they don't. 98 females said they did, and 86 said they don't. If I was to try to graph that, it would look like this. That's not really helpful to just look at the graph. It doesn't really tell me, a whole lot about this situation. And that it's for a couple reasons. Any thoughts on why? I can't really tell. Do males exercise more than females or vice versa? What might be a reason why it's not obvious if you look at those numbers? Leah?
Not a percentage?
Yeah, it's not a percentage. We don't have percentages here. If we had, notice there's 216 males and 184 females. If they were exactly equal, maybe that would work out and be easier, but it's not. What I really want are percentages or proportions. So we want percentages or proportions. These are better than what are given. In this situation, it's also important, and the idea that we're going to look at is to look at this idea of whether these two things influence each other. So like, does gender influence whether or not somebody works out more? I don't know, maybe as an adult, it might be more, I have no idea actually, but it might. You're more likely to do one thing, or if you're male versus female, something like that. This situation, when we can summarize it, is called a contingency table. And it's called a 2x2 because I have 2 rows and 2 columns. These are my rows, just to remind you, and these are my columns. What we might be interested in is whether or not these two variables are independent or dependent. So whether or not exercise is dependent on whether or not you're male or female. And that's what we're going to try to figure out. So alternatively, you might say that they are independent, which means that the gender has no influence on whether or not someone exercises regularly. So let me just write that down. Oops. So the gender of a person has no effect on whether or not they exercise regularly. So in stats, what we do is we actually approach this problem and try to see if they are independent. So we look through the lens of whether or not they're independent. And all of the stuff I'm going to show you for about the next 5 to 10 minutes is all background things that you're ultimately just going to use your calculator to do. But I think it's important in your understanding to hear it and try to take in as much as you can. So let's say they were independent, right? And you go to these numbers. If they were independent, let's say I had 110 males who regularly exercise, I would expect, if there's no relationship between gender and exercise, that the number of females would be proportionately the same. Let's say we had 200 males and 200 females. That would be a bit easier. Let's say then I expected 110 males to regularly exercise, therefore I would expect the same of the females. And that's independent, that they have no relation to each other and the proportions would be the same. So to do this, we actually can go back to what we learned in probability. And that's the probability if two events are independent, then the probability of one, remember this thing, the intersection of one event times the probability of the other go together. You do not necessarily need to recall this information, but that's really the theory behind it. If they are independent, then there is no intersection between them. Remember how we would minus the intersection? That's not the case if they're independent. So ultimately, we take the probability to find if they are, a male and exercise. We take the probability of being male and the probability of being regular exercise. These numbers come from that table. So the total number of males is 216. The number of people who regularly exercise is 208. And then we come up with what's called the expected frequency. So on the next page, if you scroll down, you get this number. This number tells me how many expected males I would have if everything was proportionate to be independent of each other. So in this case, this comes out to, if I just look here, 112.32. This, like everything else, your calculator is going to do for you. So if I just take that number, 112.32, and I go back up, and I compare it to what was observed, there were 110 males who regularly exercised. Is 112.32 close to that? Yeah, it's pretty close. It's not exact, but it's pretty close. It's as one would expect if there's no relationship between gender and exercise. So what I'm going to do is I'm going to do that same thing for all of the cells and create what's called an expected frequency table. Again, this is done for you on a calculator. I often say when I was in school, we didn't have these calculators to do this and you had to do it all by hand and it took forever. And it was very time consuming, unfortunately. So in this one, I'm just going to put in a couple examples and then we'll just put the answers. Just to give you an idea. So if I wanted the number of people expected who are female, who regularly exercise, I take the number of females times the number of regular exercisers, divided by 400, which is the total number of people, and I get 95.68. If I compare that number, if I go back up, what I saw was 98. If everything was independent, I would expect it to be 96. Again, it's pretty close. It's not far off. So I'm going to put in the other ones just as the answers. So this one would have worked out to 103.68. This one's 88, I believe, 0.32.
Wait, so what is this showing?
This is the expected frequencies table. So if my two variables were independent, meaning there's no relationship between gender, and working out, I would expect the same numbers roughly proportionate for the two. These are those numbers that in a perfect world, this is what I would expect to see if they were independent. Yep.
And so if like if we're gonna use calculator to make a table,
Yeah.
are we gonna have to create a table in our test? Or?
You will be asked to find the expected frequency, but you can get it on your calculator. So you don't necessarily need to create the table.
Oh, okay.
If you were working in medicine, you're doing your doctorate, you would,
Expected value like this?
yes, you would put it in. Yeah, like if you were doing some really official report, you would include this. But when you're just doing the calculation, it's not that bad to leave it out.
So
Yeah.
like the formula of expected value. Like,
You won't even need it.
oh.
Yeah. But I'm leading you through this process again. This will be done for you. But this is basically, so this is done on the calculator. What we want to do is, as a whole, look at all of the observed frequencies from that original table. So I'm just going to write them in. And I'm going to take the expected frequencies. So these are my observed from the original table. And these are the ones that we calculated. So these are my expected ones. And I'm going to look at the difference between them as a whole. And you might recognize this kind of looks like, when we do it, like the standard deviation. Remember when we guessed celebrities' ages and the difference between their age and their actual age, and then we subtracted them and we found a number? This is kind of like doing that. So if I put these all in,
And you have these from your calculator?
it would all be done for you.
Okay, so,
I'm just showing you the process,
yeah.
but in the end, you don't have to reproduce this. So I would take the observed minus the expected, and so some of these will be negative because the expected was below, or above rather, and they actually end up being the same. In order to compensate for the fact that some are negative and some are positive, we square it. And so you end up with this 5.3824, which is the same for all of these. It's really the last column that's really important. And this really measures the percent error between the observed and expected. So this is like my percent error. For those people who are in bio or chem or physics, you often look at what you did in your experiment versus what you would have expected in a perfect world, and then you figure out the percent error. This is that. We're really looking at, is there a big difference in what we observed versus what we would have expected if they were independent? And so these numbers, and again, I wouldn't worry too much about them, but as a whole, I want to know how far off my observed are or were from my expected. So you can just copy these numbers down. And then as a total, this number is more important. This is like the whole percent error of all of your categories and the numbers from those categories versus the expected. This is what's called chi-squared. Chi, pronounced like this, it's spelt C-H-I, but pronounced like this, K-I. So chi-squared is an interpretation of the percent error of expected versus observed. So what the heck does that mean? That's what we're going to talk about.
but how are we supposed to calculate?
You'll see. It's actually pretty easy. You're going to use some new functions on your calculator. So in a second, we're going to do that. So that number, the chi-squared, here is the formula of it. Not that you're going to necessarily have to use this, but maybe in university you will. It's really the difference between observed and expected. Let's write down that chi-squared value again. 0.217 is what we had.
This formula, if like, in which areas is it used, like in university?
So it's all within stats, but if you were to do a major in bio, for example, you would 100% be using chi-squared at some point. if you were to do, even in chem and other things, if you were to do a master's in sociology, you likely would come across this kind of stuff. So like Mr. Triol was doing a master's in education and he was using this kind of stat. So it's useful in various different areas. It really applies to different things. And we'll talk about some of them, and we'll actually use some of the data that we collected to do this for it. So this percent error is pretty small, right? Like it's not that far off of anything close to zero is going to mean. So this small value for this calculated one generally indicates that the variables are independent. So there's not much difference between observed and expected. Therefore, there must not be a relationship between the two variables. Conversely, if this was a larger value, we would say that the variables are dependent. The question is, well, what's a large enough value to say that they're dependent? And that's what we're going to get into next. Before we do that, we're going to try this on our calculator. So let's take out calculator, and you can do this on the iPad one if you have it. It's not as good, but it still works. So I'm going to open this up, clear this out, get my Dominion Lending mortgage expert at the top here. That's great, free advertising. And you are going to go into the matrix function. We're now entering matrix. If you go second function in matrix, which is the x to the negative 1, you should see matrix is below math, the math button. So I go second function, this one.
What's the other one above Zoom?
What? Zoom?
No, but what's above that?
This one?
MTRX.
Oh, yeah, I don't know what that is. Maybe you can get into it from there as well. That's a good question. If you press the green one and then that.
Not the same.
No. So in here, you will see probably blank things in there. You're going to scroll over to edit. And you're going to press enter on matrix A. Up here, you probably have a 1 by 1 if you've never used this. We're going to make it 2 by 2. So 2 rows and 2 columns. And what I'm going to input into it are the values not from the expected, but always from the observed. So we're going to put in the observed values from gender and exercise. So I'm going to type 110, 106, 98, and 86. Matrix literally means just an array of numbers in some sort of organized fashion. So popular movies called The Matrix, slightly different. Does everyone have that in? Good movie, though. So success back there. Great. Now you're going to go to another new area, although it starts in stat. So click stat. We've been there before. And scroll to tests. Within this section is a whole bunch of different tests that you will likely use at some point in your academic career. But we are going to use, I'm just going to scroll up because it's quicker. We're going to use this one. You will actually have the chi symbol. It's not X, it's chi, but you should see chi-squared test. If you press enter, you should see something like this. It's slightly different on the online calculator, but something like that. What it's going to do is it's going to do the calculation, everything we just did before by hand. It's going to take the observed values, do the calculation, and it's going to pump out the expected values into matrix B. So I go enter, scroll down and go to calculate, press enter, and there it is. It gives you the chi-squared value, as long as I inputted it correctly, of 0.217. That's what we calculated by hand. We're amazing. It also pumps out 2 other numbers. The p-value we're going to use. This other thing, df, we don't really need. It's called degrees of freedom. I don't care if you know what it is, but you don't really need it. Any questions on how to do that? Just so you see, if I wanted the expected values, which you should be able to access, go back to the matrix, and you should now see in matrix B, it says 2 by 2. If I scroll over to edit and then go to matrix B and press enter, it will show me the expected values that we calculated right here.
Will we need those?
You will need them. So everything's done in the calculator for you. You just got to know where to access it. So my expected values went into matrix B, and if you scroll on them, you'll see them as whole values, or the full value. You're going to get lots of practice on that, so I wouldn't worry too much about it. Great. This p-value we're going to talk about next. So we said, okay, great, I got this percent error of 0.217. Does it mean that those two things are independent or dependent? And this is where we get into what's called the significance level. In stats, when we do these things, we're never 100% sure that this didn't happen just by chance. In stats, there's always some sort of potential that it was just lucky in the sample that I took. That maybe the sample I took indicated that they are independent, but they're dependent, or vice versa. So anytime you take a sample of a population, there's always going to be room for error. And so what we want to do is move into talk about the significance level that we can be confident in our results. And down here, we express this significance level often in terms of 10%, 5%, or 1% significance. What that means is that you are either 90, 95, or 99% confident in your results. You're almost never going to be 100%. It's not going to happen because there's always chance it wasn't just due to randomness. This symbol, which you've seen before, little fishy, alpha, you saw probably in trigonometry, this is used to tell you the significance level. And it gives us a measure to compare the chi-squared p-value to. So this is my significance level. This will always be given to you in a question. So they'll tell you, calculate chi-squared based on a 5% significance level. If you were to go out and do your own research one day, you would decide what significance level you would want to use. For example, if I was to do medical research and I'm trying to show if something cures some disease, I would probably want to be really confident, and I would use a 1% significance level, which means I'm 99% confident in my results. So this is often used in medicine, but this is the standard significance level, which is 5%. And we use those as decimals, so 10% is 0.10, 5% is 0.05, and 1% is 0.01. Question, Leah?
Yeah, what's the p-value?
So the p-value is the probability, that's what we're going to get to next. It's the probability that the two variables are independent. And we're going to compare the p-value to the significance level. Again, pretty heavy stuff. I included this graph here. We can talk about it if you want to, but you don't really need to reference it at all. So that other thing, the p-value, that's really the important number we're going to compare to. P, and definitely highlight this, p-value is provided, which gives the probability that the variables are independent for values above whatever the chi-squared value is. The p-value can then be compared with the significance level to conclude whether or not the variables are independent. Sounds complex, but ultimately you're going to come down to this. If the p-value is small, it's probably good. It means that because your experiment result is not because of some chance, or at least on a 90, 95, or 99% level of confidence. So we take whatever our p-value is. If p is greater than alpha, so the probability that they're independent is greater than the significance level, we say those things are independent. Conversely, if the p is less than alpha, i.e. p has to be pretty small, I would say that the two variables are dependent on each other. This little part here, very important.
What happens if they're equal?
They almost never will be equal because your p-value will always go to a decimal. So it'll go down. So you always will be slightly above or below. But the closer you are to it, kind of says, oh, maybe they are dependent. If you're getting an independent result, it would be really close. And you would probably want to investigate it further. So for example, let's say at a 5% significance level, so alpha is 0.05, I get a p-value of 0.06. It's really close. What would you conclude in that scenario? Is p greater or less than alpha? Yeah, so p, I would say, is greater than alpha because 0.06 is greater than 0.05. That would tell me that they are independent. Let's say I had the same p-value of 0.06, but I changed my significance level to 10%. So now this would be alpha equals 0.10. This time p is less than alpha. And I would say that the two things are dependent. People who are out there doing these studies have to declare their significance level before they do the study. Because otherwise, if I wanted the two things to be dependent, I'd probably change my significance level to 0.1, which you're not supposed to do. You're supposed to stick with whatever you think you want to be the confidence level and then go with it. Yep, Gabe?
Is there a chance like for it to be equal?
If they are, it's going to be, you should with the p-value always get more decimals. So it will either be slightly larger or slightly less. But sometimes it's going to be close. If it's close, like I was saying, it's probably a good idea to do more studies on whatever that thing is. We're not going to do that, but that's what should happen, yeah. Great. Okay, so we're going to try an example. These steps are the very formal steps that you would know if you were doing this in a formal way. I'm not going to be too worried about those, but I am going to talk about this thing, which is the null hypothesis. At the beginning of the lesson, I said this is the beginning of the branch of math called hypothesis testing. And your hypothesis testing is always going to use this format for chi-squared tests, which says my null hypothesis, which is given this notation of h sub 0. My null hypothesis, which is what I'm testing this for, is that the two variables are independent. Conversely, my other hypothesis, which we call the alternate hypothesis or alternative hypothesis, is h sub 1. And it will always be that the variables are dependent. And that's how we're going to kind of classify them. Everything else in between, I'm not too worried about. We're going to do them kind of logically. So let's try this example down below. It says, let's say a survey was given to randomly chosen high school students from years 9 to 12. Years is really grade. On possible changes to the school's canteen, the results are shown in the contingency table on the right. It says at a 5% significance level, test whether a student's canteen preference depends on their year group or their grade. Yeah. So, we want to see, do grade 9s tend to want to change the canteen, or does grade matter at all? We're looking at whether or not the two things have any relationship, or dependent or independent. So the first thing I would do is I would state my null hypothesis. My null hypothesis, h sub o, will be that the two variables, in this case canteen preference, and I'm going to say grade level, are independent. My alternative hypothesis will be that canteen preference and grade level are the same, but are dependent.
What's the point of stating it if they always have to be one of them?
It's a good question. you're always referencing the two variables that you're talking about. In other hypothesis testing, it's not this simple. It gets a bit more complex. So this is kind of the formal way to do it. This is kind of like step one. Step two would be to state your significance level. In this case, they asked for a 5% significance level. So I would say alpha is 0.05. Everything else we're going to do on our calculator besides the final statement. So steps 3, 4, 3 to 5, we're going to do on the calculator. So let's try this one. So let's get out matrix. Let's get out of here. Go back into your matrix function. So second function and then the matrix button. And I'm going to go to edit. Edit A. This time, it's not a 2x2 contingency table. What is it? 2 by Kleenex? Oops, sorry. 2 by 4? Great. And if you screw that up, you'll notice that doesn't look right. But yeah, 2 by 4. So let's type in these numbers, 7, 9, blah, blah, blah. Once you get them typed in, then we're going to perform the chi-squared test. So we go stat, test, scroll all the way to your chi-squared test. And we go down to calculate and we press enter. And I'm going to write these things down. I get a chi-squared value. Did you get the same thing? 5.81?
Yeah.
Great. We'll round it to 2 decimal places, let's say. My p-value is 0.121. And my degrees of freedom, not that you really need to know them, is just 3. This is not super relevant for what we're doing, but it's okay to keep it. So my next step is to interpret this. Is p greater or less than alpha?
It's like greater.
Great. So I've got p, which is 0.121, is greater than 0.05. What does that tell me? Close. That part's going to take a little while to remember. So if you're going to be independent. So the probability that they're independent is small. It means that it's 1 point or 12%, 12.1%. So therefore, the canteen preference is independent of grade level. And I should include at a 5% significance level. Which suggests in this case that there is no relationship between these two things. Does that make sense? Ish?
So why does it reject? So if we reject H null or
Yep.
then we would have a step 7.
Well, no, we would here, I would say P is less than alpha, and I would say that we don't accept our null hypothesis, and we would therefore say that on a 5% significance level, they are dependent.
So for H6, can we just say H null is correct? Or for step 6, I mean.
Well, there's a bit of formality to this process in that we can't even conclude. All we can do is say that it suggests that this thing on this level of confidence. So that what we're saying here is that this suggests that they're independent at a 5% significance level. The only other thing I'm going to add to this is that there's one caveat. If you don't have enough data in each of the categories, it basically becomes invalid. And what that means is that you have to check to make sure your expected frequencies are above 5. So expected frequencies must be above 5 to be valid. Generally, if your observed values are below 5, your expected frequencies will also be below 5. The reason is, if you think about it, if I only have 2 people, take this example, 2 people in grade 9 who voted change, maybe I didn't have a big enough sample size. So you often have to have a large enough sample size in order to make it valid. And that's true in all stats. So here, the sample size has to be large enough. There's one question in the homework where you're going to explore that. And there's a way to deal with it, but I want you to try it. So the little assignment you're doing, not that I want you to do this because we're kind of doing it a bit too late, but a lot of the time you can organize your data to do a chi-squared test. For example, I know a lot of people are doing days of exercise. You could say, okay, I'm going to make 2 categories. People who work out 4 or more times a week, or people who work out less than that. And then I'm going to compare that to, let's say, height. Do tall people work out more or short people work out more? And are they independent or dependent? So you would group your data twice. So for height, you'd have tall versus not tall, or whatever you want to say. And then working out versus working out less. And then you would count the number between all of those in a little matrix like we did with that table. So we'll try that next class once you've got some practice using just the calculator. But you really can break a lot of things down into these categories where you have like low and high or something else to see if the 2 things are related. So it really is applicable to a lot of different things. Okay, try these practice questions.